Okay, let's dive right into this. Welcome to this explainer on a truly fascinating new frontier in neuroscience, the Brain Kinematics Model, or BKM for short. Today, we're exploring a radical concept that completely reimagines how human consciousness actually operates.
For decades, we've used a very specific metaphor to understand ourselves. We always ask, is your brain really just a computer? It's like we've been conditioned to think of our minds as this biological hard drive that neatly stores files in specific locations, retrieves data on command, and processes inputs through these rigid, fixed wires. But what if that traditional assumption is fundamentally missing the mark?
Well, the old view tells us the brain is just a static information storage device. But the Brain Kinematics Model, the BKM view, argues for a massive paradigm shift. It proposes that the brain behaves much more like a stretching, shifting, viscoelastic network. So instead of your memories and thoughts sitting passively in some mental folder, your brain activity actually emerges from what researchers call dynamic strain configurations.
So, the crucial point really boils down to this. The brain does not simply store information. It continuously reshapes a dynamic configuration space. It is absolutely not a warehouse. It's more like a shape-shifting geometry of connections that's constantly bending and reacting to the world around you.
Here's our roadmap for this explainer. First, 1. The dynamic brain network. Then, 2. Routine versus chaos. 3. Memory is a shape. 4. The director and the dream. And finally, 5. The measurement challenge.
Section 1. The dynamic brain network.
Right, so the core definition anchoring this entire theory is the strain configuration. I want you to imagine your brain tissue and its billions of connections not as a rigid circuit board, but as a flexible, viscoelastic strain field. When an input arrives, the brain literally bends, stretches, and routes connections in response, creating a temporary geometrical state of neural activity.
You see, an input doesn't just hit some isolated, quiet center. It perturbs a network that's already buzzing with your sensory inputs, your existing memory topologies, emotional state, cognitive context, your current stress, and even your temporal history. BKM essentially captures this collision of forces in a single dynamic equation. Literally every single thought you have is a real-time negotiation of all these ongoing variables.
Moving on to Section 2, routine versus chaos.
So how does this network actually react to different levels of stress? Well, under low-stress inputs, like a familiar commute or a casual chat, the brain's strain response is mostly linear and smooth. It uses localized pathways and stays pretty near equilibrium. But under high-stress inputs, and that could be sudden panic, deep trauma, intense emotion, or honestly even a sudden flash of creative insight, we see a highly nonlinear response. The stress acts like a tidal wave, forcing a complete, chaotic network reorganization. And this brilliantly illustrates why routine feels effortless, but sudden insight feels like a mental earthquake.
Watch how this complexity snowballs as it moves through the cortex. A simple sensation starts out with very low nonlinearity, but as you process it, perception kicks in, integrating the pattern moderately. Then, feeling amplifies it dramatically. By the time it reaches top-level cognition, what started as a tiny, simple sensory trace has exploded into a massive, highly recursive, abstract storm.
Which brings us to Section 3. Memory is a shape.
I want you to consider this quote for a second. Memories are not static objects stored in isolated locations, but stabilized connectivity strain topologies. Let that sink in. Memory isn't a box in your brain. It's a relational geometry. It is a highly unique shape formed by connecting emotional, spatial, and semantic nodes. When you remember something, your brain is actively reconstructing that physical, topological shape in real time. And because memories are literal shapes in this model, their complexity varies wildly. Down at the base, a fleeting sensory trace is a very simple shape. But as we move up through working, procedural, and episodic memory, the geometry gets immensely richer and wider. And at the very top sits our self-identity. Your sense of self is perhaps the most complex, highly distributed shape your brain maintains.
Now, you might be wondering, why do some of these shapes fade away while others seem to last forever? Well, emotion acts as an amplifier. A heavily emotional experience drives a much deeper strain into the tissue, which stabilizes the shape against degradation. It perfectly explains why a traumatic event or an incredibly vivid, joyful childhood moment stays locked in your topology for an entire lifetime.
Section 4. The director and the dream.
With all this shape-shifting chaos circulating constantly, what's actually managing the network?
BKM points directly to the prefrontal cortex, the PFC. It doesn't just invent thoughts out of thin air. It acts more like an executive director. It receives competing configurations from all across the brain, compares potential pathways, inhibits the unstable impulses, and ultimately stabilizes a temporary goal. It essentially chooses the single best strain orientation to guide your immediate actions.
Which sets us up perfectly to answer a very relatable question. Why are dreams so incredibly weird? I mean, if our waking minds are typically kept in check by this director, what on earth happens to this topological network when we fall asleep?
Well, when you go to sleep, your PFC, that executive director we just talked about, largely goes offline. That results in weakened executive stabilization. Without the director there to inhibit competing pathways, your neural topologies just propagate freely. Emotional networks completely dominate, and reality testing basically vanishes. So your memories, fears, and random concepts blend together unconstrained, generating the wild, impossible geometries and symbolic blending that we experience as dreams.
And finally, Section 5, the measurement challenge.
Now, for an elegant theory like this to actually survive, it absolutely has to be testable. We know BKM is a brilliant unifying framework for complex things like memory, emotion, and dreaming, but the primary scientific critique is totally fair. Physical strain can't just be a cool metaphor. It has to become experimentally measurable. The path forward requires neuroscientists to find concrete correlates, things like synchronization dynamics, graph topology, or neural manifold geometry, to prove that these energetic states actually exist in the brain in real time.
Which leaves us right here with this final, incredibly provocative question. If the mind is truly a dynamic shape, a living, viscoelastic topography of memories and emotions that's constantly shifting, how do we invent the exact tools needed to measure it? It's a profound challenge and one that might just shape the entire future of neuroscience. I really hope this explainer has completely shifted how you view your own thoughts today. Keep exploring, and thanks for joining me.